All right. I know that chapter 6 is sort of a long slog. To me, it's like 2 chapters rolled into one, just the sheer number of different cases and we've got new forces like the spring force and whatnot. But I wanted to go back and do an example before we continue on. We're going to talk about conservative and non-conservative forces and how to deal with them today. But I realized that, at least in the worksheet I think I printed out for you, it didn't have a spring example in it unless I skipped over it. Is there a spring example in your worksheet? I don't think so. We've got the small ice cube. No, I don't see one in there. So I wanted to do a spring example. For some reason, I had one in my PowerPoint slide here. And I thought it was a good time to just remind ourselves where we were. We had the second work energy relation where we're now only concerned with the net work done by only external forces, and that's equal to delta change in kinetic energy plus the change in potential energy. And we have these 3 potential energy functions, and we're going to focus in on the spring potential energy. And remember, a spring, a generic spring is of the type that can be compressed and stretched. And this particular, well, the force law, I thought I had someone's reading response on this question, but there was somebody asking a question about why there was a different law for when it was stretched than when it was compressed. But exactly the opposite is true. It's the same law. The same law always looks like this. When we have a spring, we mark some point on the thing that's attached to the end of the spring, and we say the stretched spring direction is the plus x direction, and we just watch where that point is as we stretch it or compress the spring. And by definition, the important thing is that when the spring is totally relaxed, that's supposed to be this middle position here. When the spring is completely relaxed, wherever the point we're marking, we call that 0 on the x-axis. So x's that are positive, that's a stretched position. X's that are negative are compressed positions. It's the same force law, no matter whether you're stretched or compressed. When you're stretched, this is saying this is the x component of the spring force. When x is positive, the spring force x component is negative, and that means it's pulling back in that direction. But when x is negative, we get a double negative, which makes it positive, and that means the spring force is pushing in this direction. So there's really just one spring force, and at this point, we're not using that, but we will think about that a little bit more later on. But we're rather just using the potential energy function associated with it, and that is saying that K is the spring constant. That just tells you how stiff the spring is. Big K means springs are really hard to compress or stretch. And the 1/2 kx squared is telling us whether we stretch it to a positive x or compress it to a negative x, we're putting positive potential energy in it either way, right? So you're storing energy in the spring, whether you compress it from equilibrium or stretch it from equilibrium. Now, for some reason, my slides are out of order, so excuse me flipping back, trying to find the place where the example is that I wanted to show, and it is right here. I thought this was going to appear in your worksheet, but this is not in your worksheet. But let's just talk about a spring example problem. And if you were in lab yesterday, or when you're in lab tomorrow, you'll see more examples in the problem solving part that I put at the end of the lab exercises, just to try to keep us practicing with more problem solving before the exam next week. So here we've got a spring attached to a rigid wall right here. And that means the only thing that can move is this mass, and the mass is attached via a spring to the wall, and the floor is frictionless. So it slides perfectly easily along the floor, but the spring is exerting a horizontal force on it as it slides. We're told the spring constant is 200 newtons per meter. That just tells how big the force is if you compress it by a meter, stretch it by a meter. So the question is this: if we stretch it by 0.4 meters from the spring's equilibrium position, then release from rest. I know I just wrote that in there, but the idea is I stretch it and then with my hand and then let it go. So right after I let it go, that's my initial condition. What is the mass's speed as it passes the equilibrium position? right? So it's like, I don't know if I can demonstrate it with this one, but it's like spring's relaxed, I stretch it by 40 centimeters, and then I let it go. And the question is, when it passes that equilibrium position, how fast is it going, right? When the spring is relaxed again, it's going to keep going past there. It would start to compress after that, but we're just concerned when it passes the equilibrium position. Okay, so we need to define a system. I just want to practice with our usual, the same work energy relation we've been working with the last couple of days of class. We're going to take our system to be everything in this case. That means essentially, if you wanted to put it into words, the things that matter are the mass and the earth, and there's an internal spring force that connects the two. So I'm taking that spring force to be internal. That means that instead of having to calculate the work done by it, it's not external, it's internal. Instead, I'm going to use the potential energy formula that we know. Okay, so let's flesh out this equation a little bit. What other forces, if I take that spring force to be internal, what other external forces are there? Well, there aren't any other external forces doing work. Now, there is a gravitational force acting. It's acting as a normal force on this, but it's not doing any work as this thing slides like that, right? Sorry, the weight force. There's a weight force and a normal force, and both of them technically are external forces. I didn't list them in, but in any case, they're not doing any work, and there's no change in potential energy, right? This isn't going up higher away from Earth or lower down. That would be the only case you get a change in the gravitational potential energy. Gravitational potential energy is just constant. So the only potential energy that's changing is the spring. No external forces are doing work. So this is 0. And then I go into brainless mode. I do 1/2 mv final squared minus 1/2 mv initial squared. If you wanted to, you could do mg y final minus mg y initial, but y final and y initial would be the same. So that just goes to 0. The important thing is I need a 1/2 k x final squared minus 1/2 k x initial squared, where x equals 0 means when the spring is relaxed. So that means that x final, I'm going to take final to be when it's passing the equilibrium position while it's contracting. And x initial is when it's just after it's released from rest. So x initial is 0.4 meters, I believe. I know it's kind of small up there for those of you in the classroom. And x final is 0. That's why I'm sort of throwing that away. It's released from rest, so v initial is 0. And we want to find v final. So that's our variable to solve for. Nothing more complicated than the kind of stuff we've been doing. Just solve for v final, and I get 8 meters per second. Just as an example of using that. Any questions on that one? We're still not done with that worksheet, so hopefully you have that worksheet. I have a few more copies if we're going to work with some other stuff in the worksheet to finish it up today. Okay, so here's where we are. I want to go back and talk about something that I sort of just didn't mention at the time we were doing it, but I did something that didn't make a whole lot of sense for all forces. And we haven't looked at the kinds of forces where it really makes a difference so far, but there are forces where this isn't going to work. You may or may not remember that back when we talked about, two masses connected by a springy force or something like that, we did a derivation. And at one point in the derivation, we said, we're going to separate out the forces that are acting on these two ends of the object into external forces and internal forces. Okay, so in this example, I was pulling the two masses out with my hands, and I was saying, let's treat those as external forces, but the spring force is internal. So let's divide up. Uh-oh. I need to click on this again so my pointer will work. Let's divide up the net work done into external and internal forces part. And we did something that seemed totally harmless. We put this internal part over on the other side with a minus sign. And we said, let's take that negative of the net work done by internal forces. We'll just call it the change in potential energy. Just a definition, right? Shouldn't make any difference. So I'm going to question that now. Does it really make sense to say a change in a potential energy is equal to the negative net work done by internal forces, or the final potential energy minus the initial potential energy is the work done by internal forces? It's suggesting that the work done by internal forces somehow just depends on the initial configuration and the final configuration, but it doesn't depend on how you get from the initial to final configuration. If we're going to write this, the work done might depend on exactly how you transition from initial to final, but the left-hand side clearly just depends on the final state and the initial state. It doesn't know anything about how you got between them. Okay, so in general, you can't do this. In general, the work done by an internal force might depend on how you got there. Okay, but in a lot of kinds of forces that we find in physics, and in fact, all of the ones we've talked about so far in the context of delta Ke and delta Pe, the gravitational force, the spring force, those are examples of what are called conservative forces. And conservative means that the work done by that force does not depend on how you got from the initial state to the final state. It only depends on where you started and where you ended up. And it's worth doing some examples of that. Let's do an example of a conservative force and a non-conservative force. The claim is the gravitational force is conservative. So let me imagine, here's a block. I'm going to take my system to be this block plus the Earth. And the gravitational invisible spring between them is an internal force for me. Okay. And I want to calculate the work done by that gravitational force as I bring it from rest here to rest up here. Now I could do that in a lot of different ways, right? One straightforward way to do it is just to move it up at constant speed past that point up at the top, right? And then I would say, clearly, the gravitational force is doing positive, negative, or zero work as I lift it up like this. I'm talking about the gravitational force. Negative, because I'm moving it up and the gravitational force is pulling down. So that's the hallmark of negative work. That's only one way I could get from rest here to rest up here. Another way I could do it is to say, well, let me move it over here, and then I'm going to go and overshoot the point I want and come over here and then come back down, and then I'm finally at rest. That's another way I could have gotten from the initial state to the final state. What about the work gravity does there? Well, let's see. Gravity did zero work. Then it did too much negative work, right? Bigger than the amount we got before because it did more negative work. It went to a higher height. I was only stopping here before, right? And then it did some more zero work. And then it did some positive work. And if you work it out, the change is going to be the same. It doesn't matter whether I go straight up, whether I go along some really tortuous path, as long as I end up in the final state and we're talking about the gravitational force, it's going to do the same amount of work. Okay, so it's by definition a conservative force. What about a non-conservative force? Well, a typical non-conservative force is the friction force. Let's imagine a very similar situation where I've got initial state is block at rest over here. Final state is block at rest over here. Nice simple states. So one way I might get from initial to final is maybe the system moves like this. So if we're, maybe my system is block plus table, and the friction force between them is an internal force. I'm going to take it to be internal. Okay. What is that? What kind of work is that friction force doing as I move it over here? Positive, negative, or zero? It's negative, right? Because I'm pushing in that direction. Friction's always pushing back against the direction you move. So it does a certain modest amount of negative work. Now let's imagine that instead of going straight over there, I take this block and I move it down in this direction. Has friction does positive or negative or zero work so far? I just moved it sort of along a curve over here. I slid it along a quarter of a circle, let's say. Well, let's think. For each little step it takes forward, friction is always pushing back exactly opposite the direction of motion. So that's a little bit of negative work, right? So it's going a little bit of negative work, 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 and so on. Now I'm going to keep moving it around like this. As I move it around on this long path, it's always doing negative work the whole time. And so when I add up all that negative work and end up over here, it's definitely going to have done a lot more negative work than it did in the first case, right? Because it's always pushing back along that whole curved path. So it's what we call a non-conservative force, which means that not only do I have to tell you where I started and where I ended up for the system, those initial and final configurations, but how I got there. That's the kind of force for which we can't do this definition that's shown up at the top here, because this clearly depends on how we got between the initial and the final, whereas this suggests that there's a function that I just have to evaluate the final state and evaluated the initial state, and somehow it doesn't know anything about how we got between them. So we can't make that redefinition. In other words, you're not going to be able to find a potential energy function associated with the friction force. There's no such thing, because it would have to have lots of different values for the same initial and final states. Okay, so that's the idea of a conservative versus a non-conservative forces. And so in that derivation, that last step where we redefine the negative of the work done by an internal force is the change in potential energy can only be taken if the force is conservative. Okay, so let's go back through the derivation again. We divided up our forces into external forces and internal forces that were doing work. Now we're going to have to further subdivide the internal forces into internal conservative forces and internal non-conservative forces. And for the conservative ones, it's perfectly okay to move that over with a minus sign over here and make the redefinition as a change in potential energy, because a conservative force doesn't care how you got between initial and final. It just cares about the change in something. We're just going to call that potential energy. But this one over here, the non-conservative internal forces, I'm going to have to leave on the left-hand side. I really wanted to have only external forces over here. Now, I'm certainly welcome to put it over on the other side with the minus sign, but I can't redefine it as a change in potential energy, because that's suggesting it only depends on the endpoints, the initial and final, and clearly for a non-conservative forces, it probably doesn't. Okay, so this is yet another almost the same but slightly more subtle work-energy relation, which is saying only for I may have several internal forces. Maybe one of them's conservative and maybe one of them's non-conservative. I might be talking about something falling through the air, and gravity is an internal force and air resistance is an internal force. One's conservative and one's non-conservative. For the conservative one, I'm going to just treat it as a change in potential energy on this side. For the non-conservative internal force, I'm just going to leave it over on this side. Or you can put it on the other side with the minus sign, but you can't change it into a potential energy. There is no potential energy function associated with it. Yeah, sure. We'll see this boxed equation appear in my running list of work-energy relations in just a second. I've been trying to develop a running list and keep building on it as we go on. Okay, so what are some other conservative forces? A lot of the ones we've been talking about: gravity, the spring force, which is called Hooke's law, as you know, that's a conservative force. The idea is it doesn't matter in going from, say, relaxed position to a stretched position, the spring force is doing a certain amount of negative work as it goes from there to there. And just like the gravitational case, I may overshoot and it does too much negative work, but then it does a little bit of positive to get back to where I ended up in the other case. And so it really doesn't matter which way you go, as long as you have the same initial and final state, the force does the same. Electric and magnetic forces between charges and currents, those are things that we're not talking about in this course. We used to 8 or 10 years ago, but then we changed what was in physics 110. So in typical non-conservative forces are the ones you think of as dissipative or frictional forces. Friction and air resistance are the typical ones there. And the other forces that we've talked about, normal forces, well, they just don't do any work at all. And so I would typically make them external, and then you get a zero contribution from them, right? I'm trying to think of what other forces we've talked about besides normal forces. Normal forces is another typical one that might appear, and I would always make it external, because if something's sliding, the normal force is doing zero work because it's always moving perpendicular to the normal force at any point. Okay, so again, here's our running list of work-energy relations. Our good old friend now, the work kinetic energy theorem. Man, things were so easy when we were just dealing with rigid non-rotating objects, a particle. Then we took springy systems, and now we've just found out that Well, this really only works. We can only write it in this simple way if the internal forces are only conservative forces. And those are the only cases we've studied so far. So we haven't really done anything wrong so far. But in the more general case where we might have some non-conservative internal forces and we might have some conservative internal forces, typically we would put the conservative internal forces works over on this side as potential energies. And we would leave the non-conservative forces over on this side. And someone generally has to tell us how much work did air resistance do? It's a hard thing to compute. So someone might just say, well, as this ball flew up to its highest height, maybe air resistance did minus 20 joules of work or something like that. Okay, let's do some example problems. And I hate it when I'm in a presentation and I get surprised by something that appears up there, but that's what happens when you have long presentations. Okay, so this has to be calculated for each non-conservative internal force, and we should have a separate one of these terms for each internal conservative force, right? We might have something where we have a spring mounted vertically and a mass is compressing the spring, but it's also going down in the gravitational field. So we might have a gravitational potential energy and a spring potential energy in the same system. We'll see an example like that. Okay, let's look at the last problems on the worksheet. Anybody need a copy of the worksheet? I have a few extras just because so many people were missing when I first handed it out. This is the same one, I think, that was from, was it posted for last Friday's class date? I think we've been chipping away at this for a while, but I'm looking at problem 4 on the back side. And let's do this one together. And in fact, let's just do it at the board so it's not too fast on the slides here. Take a break from the slides. All right, so we've got a ½ kilogram ball launched upward with a 30 meter per second initial speed. That's my initial state. Suppose that as the ball rises to its maximum height, air resistance does minus 50 joules of work. Again, using the system everything. That means I'm going to take all forces and make them internal. So as the ball moves up, there's a gravitational force on it. So I'm going to take the ball plus the earth to be part of my system, and the internal gravitational force will be an internal force. And I'm also going to take that air resistance force to be internal. Okay, we're throwing all forces on all moving pieces into the system. And the question is, find the maximum height above the launch point that the ball reaches using energy methods. So we're going to take the final point to be the point when it momentarily comes to rest. Not just due to gravity, but air resistance is sort of pushing back on it and doing negative work. Okay, so our new work energy relation is the net work done by external forces plus, the net work done by internal non-conservative force. I'm being really sketchy with my subscripts, but I don't want it to get too big. Internal non-conservative forces we have to keep on this side. And that's equal to the change in kinetic energy plus the change in potential energy. Now, I've made the only significant forces are gravity and air resistance. Air resistance doesn't have a potential energy function. So the only one I'm going to include here is the gravitational potential energy. The air resistance has to be included in this non-conservative part that I left on the left-hand side. Okay, and my system, I'm including all forces inside the system. So I'm just summarizing that by everything. So how much work is done by all the external forces? Yeah, if I've thrown everything into the system, there aren't any other external forces. Everything that matters is in the system. So the external forces are doing zero work. How much work is done by internal non-conservative forces? Well, so gravity is a conservative force, so that's not going to come into this term. The conservative forces, in most cases, we're going to put over here. We could leave it as a work on the other side, but most of the time it's just easier to use the potential energy in these cases. So my two forces that are internal are gravity and air resistance, and the only one that's non-conservative is the air resistance force. And we're told here that it does minus 50 joules of work. That would be, we don't in general have a good way to calculate how much work air resistance does. So that's either something that will end up being your variable you solve for, or something that someone just hands to you on a silver platter. This is the latter case.
Dr. Kelly,
Yeah.
in the previous slide, was it W net by external plus, or was it minus W net by internal?
Plus.
Okay, okay.
Because
Thanks.
this all came from having the network done by all forces. Then we divided into internal and external, and then we divided the internal into conservative and non-conservative, but they were all added together on the left-hand side.
Okay.
So this was an internal force that we didn't bring over to this side by subtracting it off, because
Got it.
no potential energy. All right, brainless mode, 1/2 mv final squared minus 1/2 mv initial squared. The m is the mass of the ball that's going up, right? And gravitational potential energy, the ball is thrown up at a modest speed, so it's going to stay close to the surface of Earth. What was the speed? 30 meters per second. It's not going to go, outside the atmosphere or something like that. It's not going to go that high. So gravitational potential energy that's relevant is the mgy, where plus y is always up from the Earth. So I would write this as mgy final minus mgy initial. Got to make sure I'm not going out of view here. Okay, good. And we want to know how high it rises. How high it rises, in other words, is y final minus y initial. So you might get in the habit of just factoring out the mg when you see something like this. If you're solving for how high it goes between the final and the initial, this is my variable I want to solve for, right? Delta y. That's how high up it goes after launch until it comes to rest. So by definition, when it comes to rest in the final, momentarily, that's my final state. That's good. That means v final is 0, right? And well, look, I guess I have an m in every term on this side. There's no good reason to divide by m. I guess I could divide by m and I have only one of them over there, but I'll leave my m in there. So I have a 1/2, m is 0.5, v initial is 30, and here I have 0.5 times 9.8 times this. So it looks like I know everything except this, and so I can solve for y final minus y initial. In other words, delta y. And I get 35.7 meters. Okay. Nothing mind-blowingly different. It just, the formula looks a tiny bit more complicated because we can't associate a potential energy with that air resistance force. All right, why don't you spend, just to take a little bit of a break from the slides, spend some time trying 6 and 7. There's not much of a calculation to be done in those two cases, but they both involve friction. Looks like 6, you could use kinematics, but please don't. Use your energy methods to practice with that in problem 6. Okay, let's try them together. At least you've had a taste for how to think about it. I'm going to leave my most general work energy relation up here, and maybe we can think about it two different ways. First, I might take my system to be everything, and then later on we can just take the system to be the block and use our good old friend, the work kinetic energy theorem, because it will be behaving like a particle. But so here the situation is, oh, sorry, and I've got to unshare this screen to get it on the video. The situation is a block is given an initial push, and of course it comes to rest under the influence of friction. Perfectly ordinary kind of phenomenon. And the question is, how much work does friction do in that process? We're given the mass of the block, the speed, initial speed that we push it with, and the coefficient of kinetic friction. So let's try taking our system as everything, just to spell it out. That might mean I could say my system is the block plus table. The table is really part of Earth. I'll throw Earth in there if you want to put gravity into it. And we'll say, what are the forces that might be acting on the thing that's moving? And the forces that are acting on it are well, let's see. Between these parts, there is a gravitational force and there is a friction force between these parts. We'll take those to be internal. And I guess I'm not going to take quite everything, because I'm going to take the normal force to be external. You know, almost as if someone's hand was coming in from underneath and providing the normal force, even though the gravitational force is inside the system. Okay, let's see. So almost everything is in the system. That normal force is an external force I'm treating as going from the outside. That's the only external force. How much work is the normal force doing as this thing slides to rest on a horizontal table? 0, that's pretty typical, right, for normal force. How much work is done by internal non-conservative forces? Well, I've got gravity here, that's conservative. I've got a friction force, that's an internal non-conservative force. And that's the only one. So I could just relabel this as the work done by friction. And that's what we want in this problem, right? Isn't that what the question is asking? So if I can calculate the right-hand side, I'm done. Change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. Gravitational potential energy, of course, it's not changing gravitational potential energy because it's only moving horizontally. Its y coordinate isn't changing, but I could, you know, do mg y final minus mg y initial, but of course, y final and y initial are the same, so that's going to be 0. It's not changing gravitational potential energy, so you could leave that out if you want. Okay, what do we know about these two to simplify? Help me simplify either one of these two. Yeah, V final is 0. I'm going to take final when it just comes to rest, and initial is just after I release it, pushing it. So this one's 0. And over here, we're given the mass. What is it? 2 kilograms. So this is going to be, the work done by friction is minus 1/2 times 2 in SI units. I think the initial speed was 30, right? And everything else was 0 on this side. So let's see. 2 divided by 2 is 1. So that's 30 squared is 900. It looks like minus 900 joules. 3. Okay. That sounds like minus 9 joules then, right? Good.
Why do we have to use the friction coefficient in this problem?
Why don't we?
Yeah.
Well, you know, you could think of what happens with different friction coefficients, and you'll see that it's independent of friction coefficient. If I have a huge friction coefficient, right, and I give it that 3 meters per second initial speed, it's going to come to rest almost immediately, right? If I have a low friction coefficient, that's like I have it on ice or something, and I give it a 3 meters per second push, it's going to take a while before it comes to rest. But after it's come to rest, it had some initial kinetic energy, and this final kinetic energy is 0. The change is the same. What's different is in one case, it took a long time for friction to do that work. And in the other case, it took a very short time. We don't care about how much time it took. We only care about the total amount of work done here. So apparently we didn't need that mu k, although we will in the next problem. Is that enough, Nafiz?
Yeah, I think so.
Okay. Let's compare that. Any questions on this one before we go on to the next problem? All right, 6, a 2 kilogram block. This is the same setup, but we want to find the speed of the block after it's moved 1 meter. Apparently it goes more than 1 meter. I calculated that ahead of time to make sure I didn't make a fool of myself, but yeah, so at 1 meter, it's still moving. And oh, I forgot I was going to do this a different way, right? What if we just very quickly try to take our system to be just the block? That's our good old friend, the work kinetic energy theorem, right? Block is a particle. And so we can say the net work done by external force, there aren't any internal forces when you have a particle. So that means there's no potential energy changes. There's no internal non-conservative forces. Hey, there's the work kinetic energy theorem hidden inside this more complicated version, right? It's still in there. So it's sort of, this is just a more general theorem. And so we could say the net work done by all forces. Well, friction is the only force doing work as it slides to rest, right? There was a normal force, it didn't do any work. There was a weight force, it didn't do any work. So when we say the net work done by all forces, that's just the work done by friction. And that's equal to the change in kinetic energy, which is 1/2 mv final squared, that's 0, minus 1/2 mv initial squared. That's exactly what we did before. So it comes out just the same. We'd still get -9. Okay, so here we have this. Let's take the same system. We'll take that complicated system I did first, just to do it a different way. We're throwing everything that matters into the system, except I'm imagining that the normal force is external. If you ever have a force that doesn't do any work, you could say it's a conservative force because it does the same amount of work no matter how you get from initial to final. It's always 0, but the change in potential energy in that case would always be 0 too. Okay, so how much work is done by external forces? If I'm taking friction to be internal, the work done by external forces as it slides that 1 meter is 0, just like it was when it slid all the way to rest. It's just not quite getting to rest. The work, I need to put in the work done by friction. Okay, let's put that as a placeholder. And then I've got a 1/2 mv final squared minus 1/2 mv initial squared. And of course, there's no change in gravitational potential energy, just like there wasn't last time. It's staying at the same height. Now, in this case, v final is not 0, right? That's what we want to find. This is our variable. So I somehow need to calculate everything else in here. We're given the mass, we're given v initial, so the right-hand side looks good except for what we're going to solve for. I need to calculate this. How can I calculate the work done by friction as it slides 1 meter kinetic friction? Yeah. Yeah, we're going to use the only way we know how to calculate work, which is as long as the force is constant, and we're told this friction force is constant as it slows down, the work done by a force on an object as it's sliding is Fx times delta x. So we might draw a little cartoon here. Here's our block. Here it's going at 3 meters per second. And then over here, it's moved 1 meter. And this is our V final. Slowed down, presumably, right? So in this case, if I call plus x along the direction of displacement, the friction force has a negative x component. So this Fx is negative here. So it's going to do negative work. Let me just put in that minus sign. And then the magnitude of the x component is mu k times the normal force. And then I have to multiply by delta x, which I think is 1 meter here, right? And we're given mu k. This time we're going to use it 0.3. How about the normal force? What's that? Yeah, it's mg because the only two vertical forces are normal force and weight force. And so they have to balance out because it's not accelerating vertically. They balance out exactly. So this would be, what was it, a half kilogram? I can't remember, but it's mg in any case, times 1 meter. So I've got to, bring this over to this side and do that subtraction and then take a square root. But after you do all that, you can check your work. I get V final. Well, for some reason in my solution, I didn't show the final number, but this work done by friction is minus 5.88 joules. And then when I calculate V final, let's see. V final is going to be, I need to multiply both sides by 2, minus 5.88. I need to multiply by 2 and divide by m, which is 2 kilograms. And then I need to take the square root. Oh, I forgot about my V initial. If I multiply by 2 and divide by m, then what's left on this side is V final squared minus V initial squared. So then I've got to add V initial squared onto this side and then take the square root, whatever that number is. Anybody calculate that? I hear some calculators clicking and clacking. For some reason, I dropped the ball in my solution. I was just so happy with this work. I just celebrated and put a box around it. What'd you say? After you take the square root, so yeah, the square is gone. 1.77 meters per second. Kind of makes sense, right? It hasn't come to a rest. We pushed it at 3, right? It's not going to be less than 3. It's not going to be greater than 3, but this is somewhat down. Okay, let's do one more sort of problem that involves not friction, but actually more than one force at the same time. Pull one of these over. This one I didn't put in the slides, but we'll just do it on the board too. Here's a typical kind of maybe a launcher toy that you might build with a spring. So here's the ground. I'll just draw it like that. That's the rigid ground of the earth. And I have a spring that's attached to the ground down there, and it can be compressed. And I'm going to put a little just platform up there so that I can put things on that. And what we're going to do is take a little mass and compress the spring down and then let it go from rest. And it's going to shoot this thing up in the air. And the question is, how high does it go above where we let it go from? Okay. So this is what, so let's imagine this whole thing's effectively massless. So this is the spring's equilibrium position. So I'm going to draw a little axis on here and I'll say, this is 0. Since gravity is involved here too, right? Gravity is pulling on it as it goes up. I probably want to call this the plus y direction and think of my spring forces going along the y, 1/2 k y squared rather than 1/2 k x squared. But I'm going to measure the position of this, relative to where the platform is. That's just what I'm deciding. Okay, so initially what I'm going to do is, here's the first thing. I push it down so it's really compressed down here, right? And I put this little mass on it. I'll draw it bigger just so that you can see it. 0.1 kilogram mass. I'm just going to put a 0.1 on it, 1/10 of a kilogram. The amount I've pushed it down here relative to here is 1 meter. It's a big spring. I was able to push it down 1 meter, okay? And then I release from rest. I'll just put release from rest there. And of course, it's going to shoot up. Now, if I don't push it down enough, it might not even make it up to the top again, but I push it down far enough and it's going to shoot off the top of this. There's nothing gluing it on. So once it gets past this point, it leaves the top of the spring and the spring doesn't keep going up because the spring is not attached to it. It can't pull down on it, can only push up on it. So the final configuration, again, continuing this line over here, the spring has completely uncompressed. So it's back to that configuration. And the mass is up here somewhere. And we want to figure out what this height is from where it started to where it ended up. We might call that h. And the question is, what is h? And for this problem, we can talk about putting air resistance into it, but let's ignore air resistance to begin with. And let's take our, one of my favorite systems is throw everything into the system. Then there's no work to be put on the left-hand side for external forces. My system is going to be mass plus everything on Earth, which includes the spring. And I'm going to take the spring force and gravity to be internal. And at least we'll assume that no air resistance is acting here. Okay, and let's write down our new form of the work energy relation, the net work done by external forces plus the sum of all the works done by internal non-conservative forces is equal to delta KE plus delta PE. And then I just try to expand these things out. For my system, how much work is done by external forces? 0. The only other force that might have worked was air resistance, and I said verbally we're going to ignore that, so that's 0. Both of the internal forces are conservative, so this one's 0 too, right? Okay. Delta KE, so that's 1/2 mv final squared minus 1/2 mv initial squared. Now I didn't say what initial and final were going to be, but it's pretty clear. I'm thinking just after release, that's initial. Momentarily comes to rest at the top, that's final. Okay, so what's the initial kinetic energy? 0, because I released it from rest. What's the final kinetic energy? 0, because it's momentarily come to rest. Hey, we got a lot of zeros in here. This is looking pretty good. Now, the reason I wanted to show this problem is because we have 2 kinds of potential energy functions. We're going to have to do the change in the spring potential energy plus the change in the gravitational potential energy, right? So let's put both those in. 1/2 k x final squared minus 1/2 k x initial. And since I've aligned it along y, and plus y is along the stretching direction, I'm just going to call these y's instead of x's so I can have one axis. Y direction is the x direction. And then I've also got plus mg y final minus y initial. All right, so everything's 0 over there. I just got to work on these pieces. And notice that this is what I want. This is what I'm calling h here. So that's my variable I want to solve for. How high it went up from the initial position where I released it to the final where it momentarily came to rest. All right, I know m, I know little g, right? This is what I want. We know the spring constant. No, I didn't say what the spring constant was. What do I have it here in my notes? 20 newtons per meter. You have to be given the spring constant. So this spring constant is 20 newtons per meter. So I know the K. What's Y final for the spring? It's 0, right? The spring didn't get stretched up with the other thing. So in the final configuration, the spring has no potential energy left in it, right? If it were a really massive spring, it might have some kind of momentum. We'll talk about momentum in the next chapter, and it might leap up above there before it comes back down. But if you have an effectively massless spring, it really can't resist the spring force pulling down on it. So Y final we're going to call 0. In other words, it's back at its equilibrium position. And Y initial is, sorry, and this needs a square on it. I'm not sure how I forgot that. Y initial is -1. Right? If 0 is up here, I pushed it down to a y coordinate of -1, or that's what we normally call the x coordinate for a spring. So this is right here is -1 meter squared. The square takes care of the minus sign, but I still have a minus sign out there. Okay, so it looks like I'll get 1/2 times 20, that's 10, times 1. So this is 10. I've got a minus sign in front of it. I'm going to bring it over here. It'll have a plus sign in front. It'll be a plus 10 on this side. And that will be equal to the mass of this thing, 0.1, times G, 9.8, times H. So I just need to divide by 0.1. That makes this 100. And then divide by 9.8, which brings it pretty close to 10 again. I get the height is 10.2 meters when you actually put in the 9.8. Okay. Good. We've got 1 minute left, and let me just ask a different question. Suppose air resistance were not negligible, but I told you that air resistance does -5 joules of work on the way from release to the highest point. Air resistance is clearly doing negative work. It's pushing back against the direction it's moving through the air. What would we change in this problem? What would we add at this step right here?
W net initial would be -5.
Right. I mean, it kind of depends on whether I choose. One of these would have to then be -5. Maybe we could make air resistance an internal force, and then it would come here as a -5. If we made it an external force, it would come over there, clearly not changing anything. So if that's a -5, notice I had a 10 over here, but it would be, then this would become a 10 minus 5. So this would be 5. And so it would be exactly half of this after we divided the other stuff out, 5.1 meters. Of course, it's going to go to a less high height if air resistance is pushing back by a lot. All right, we are almost there to the end of this chapter. I think the only thing we have left to talk about on Friday is power, if I remember correctly, and that might take, half the period. I am going to put the reading for the beginning of chapter 7 for before Friday. So just keep that in mind. You might want to do it earlier tomorrow. The chapter 7, my intention is we have an exam, if I remember correctly, next Wednesday. And I'm going to make chapter 6 the cutoff for the exam. We just won't have enough time to do any chapter 7 homework. And I'll probably have the first chapter 7 homework due after the exam, so you can effectively put it off. But I do want you to do the reading just so you know what we're talking about in class. I'll post the usual videos for those initial sections as well if you're into watching those. All right. See you on Friday, if not before. And if you haven't had lab yet, you'll be doing some practice problems in lab with work energy stuff too.